Welcome to this video. In today's video, we'll be looking at circular motion or vertical non-uniform motion. You can see from this first image on the screen at the moment that circular motion does look rather confusing when it's in the vertical plane. However, let's see if we can make some sense of it. First of all, the most common scenario that enables us to examine circular motion is that of a roller coaster. So let's consider the following footage first. Okay, our first scenario we want to look at is where we have objects on the top and outside of vertical circles. So in this diagram, we have a vertical circle and we have an object on the top that's moving to the left with a constant speed. Now in this scenario, we're going to take the net force as a positive direction. So let's examine the forces operating on this particular object. First of all objects have a weight force or a force due to gravity, Fg, heading towards the center of the Earth. So we have a green force here, Fg, the force due to gravity. Opposing that is the normal reaction force of the surface upon the object. So this is now Fn, the normal reaction force. So we've got a vector addition here. The first force is the green force from tail to head, force due to gravity, and we add to that tail to head the force of the normal reaction force. When we add those two together, you can see we end up with the net force. So there's different ways of looking at this. First of all, if the net force is a positive direction, then the green gravitational force is also positive, and we consider the upwards normal reaction force as a negative. The way I look at it is the net force is the sum of the two opposing forces. The net force means that if it's heading towards the center, the gravitational force must be greater than the opposing normal reaction force. So we can write this as an equation. We can say the net force is equal to the gravitational force minus the normal reaction force, because it's going in the opposite direction. It opposes the downwards force. It's the one force that's going upwards. We all know that circular motion, the net force is mv squared on r, which is equal now to mg take the normal reaction force. Let's look at an example. So our first example is a cart of mass 20 kilograms. It's moving over a circular track of radius 5 meters at a speed of 6 meters per second as shown in figure 1. Now we take the acceleration due to gravity as 9.8 meters per second. The task is to calculate the magnitude of the normal reaction force when the cart is at the top of the track. So in this situation again, we have both the centripetal or net force going down towards the center. We have the force due to gravity going down towards the center. The normal reaction force, because the cart's on the top of the track, is pushing upwards. So we'll start with the equation that we had earlier. First of all, let's set this out. The normal reaction force is our question mark. The radius is 5 meters, the mass of the cart is 20 kilograms, and the speed is 6 meters per second. And of course, we take gravity as 9.8 newtons per kilogram, or 9.8 meters per second squared. So the equation is the net force is the weight force, both of them heading downwards. We'll consider the net force to be positive, opposed by the normal reaction force, which is going in the opposite direction, so minus the force of the normal reaction. We can transpose that. We can add our normal reaction force across to the left and then subtract our mv squared on r to the right. So I now have this expressed in terms of the normal reaction force. At this point, we can sub in our numbers. The mass of 20, gravity of 9.8, mass of 20, speed of 6, and we square it over a radius of 5. That gives me a normal reaction force of 52 newtons pushing up from the surface of the track. The next scenario we have is where objects are on the top and inside of vertical circles, or at the top of the vertical motion while attached to a string. This could be the case in a roller coaster, where a roller coaster comes along and it's attached to the track and the passengers are upside down as they move across. So again, gravitational force always towards the center. The normal reaction force, it is pushing towards the center as well. Normally that's because the wheels are attached in some capacity and the normal is pushing downwards. So when I add both of those together as a vector, clearly my net force is the sum of those two heading towards the center as well. So as an expression, the net force is the sum of the gravitational force and the normal reaction force. So mv squared on r, the net force, is equal to mg, the gravitational force, plus the normal reaction force. So example 2, a ride at the fun fair involves a car traveling around a vertical circle of radius 15 meters. The arrow indicates the direction of travel as shown in figure 2. So we have our diagram here. What is the minimum speed that the car can have at position A, up the top, if it is not to leave the rails and start to fall? Now, first of all, minimum speed occurs when the normal reaction force is 0. So it's almost, if you like, barely touching. If we consider the normal reaction to be 0, that allows us to do some good mathematics. So we want to know what is the minimum velocity that it can go around this track without falling. The radius is 15 meters. Gravity is 9.8. Our equation is centripetal force mv squared on r is the sum of the weight force, or rather the gravitational force mg, plus the normal reaction force. At this point, it looks like we're missing variables, so we don't have a mass. It appears as though we can't solve this problem. However, when we sub in the normal reaction of 0, things become a little easier. We now have mv squared on r over 15 is equal to 9.8 times m. And you can see here, when we simplify, we can cancel out the two m's. So regardless of the mass, that's not going to impact upon the minimum velocity or speed that this object can have that just goes around without falling off the tracks. So we divide through by the m's and we end up with v squared over 15 equals 9.8. So v squared is 9.8 times 15. And then we take the square root of that to find v. Take the square of both sides. It gives us an answer of 12.1 meters per second. So based on a normal reaction force of 0, this car can just skitter around the track at a velocity of 12.1 meters per second. Any slower and it will fall off the track. A quick reminder, of course, a simpler form, the minimum speed for vertical circular motion at the top is just equal to the square root of gr, which, as we see, has no mass dependency whatsoever. That would have given exactly the same answer. It really is this equation here, 9.8 times 15. Let's consider now we've got a string moving around at the top. It's also got a force due to gravity moving down. It has, this time, not a normal reaction force, but a tension force. The string generates a tension towards the center. When we add those two downwards forces towards the center together, we end up with a net force. So in this case, it looks very similar to our previous example on the left-hand side. The net force is the gravitational force plus, rather than the normal reaction force, because there is no material to create a normal reaction force, we add the tension force. So we expand that, mv squared on r is equal to mg plus the force of tension. A quick example. In an experiment, a ball of mass 2.5 kilograms is moving in a vertical circle at the end of the string as shown in figure 3. So here's our ball moving around, moving to the right, rather a clockwise motion. Calculate the minimum speed the ball must have at the top of its arc for the string to remain tight under tension. So the minimum speed again occurs in this case with the tension equals 0. So v min equals question mark. The radius is 1.5. Gravity is 9.8. The equation we have here, towards the center, mv squared on r, the net force, is the sum of the gravitational force mg plus the tension. However, when we're looking for the minimum speed, tension becomes 0. We fill in our gaps. 1.5 is the radius, 9.8 is gravity. We simplify this equation, and again you can see you can cancel out the two m's. You end up with v squared on 1.5 equals 9.8. We can multiply that 1.5 across to the right hand side, and then take the square root and we find our answer. In this scenario, with a mass of 2.5 and a radius of 1.5 meters, we find the minimum velocity that this ball must travel at is 3.83 meters per second in order for it to complete circular motion and not simply fall down. Once again, we could have used the minimum speed equation here, which is equal to the square root of gr. As we have here, the minimum velocity or speed is the square root of gravity, 9.8, times the radius. So remember this equation, definitely one for your summary sheets. Finally, let's have a look what we have when we're inside the objects on the bottom and the inside of vertical circles, or rather at the bottom of the vertical motion while attached to a string. Let's check out the force diagrams. First of all, again, center of mass generates a gravitational force to the bottom, as shown here, downwards to Earth. The normal reaction force here is pushing back up against the cart, so it's pushing upwards. Which is bigger? When we add them together, the red normal reaction force is bigger, and by how much? That gives us the net force. Again, we draw it from tail to head, the green gravitational force, from tail to head, the red normal reaction force, and then from the start to the end is our net force, the blue force. The net force and the normal reaction are moving towards the center. We'll consider those as positives. The green force, our gravitational force, is heading downwards in the opposite direction, so we'll consider that to be a negative. So as a statement, the net force is equal to the normal reaction going up, take away or opposed by the gravitational force going downwards in the opposite direction. Let's expand. mv squared on r is equal to the net force, take mg. That's the extended version of the gravitational force. An example to have a look at. Model car of 2 kilograms is on a track that is part of a vertical circle of radius 4 meters as shown in figure 4. At the lowest point L, the car is moving at 6 meters per second. Ignore friction. Then it says, at the lowest point L, draw the net force acting on the car as an arrow attached to the car labeled F net. Okay, so it's here, and we know at this point the net force is towards the center of curvature. So F net is moving up towards the center of this curve. Second part, calculate the magnitude of the force exerted by the track on the car at its lowest point L. So let's have a look. First of all, we want to work out the force exerted by the track on the car is another way of saying the normal reaction force. The mass is 2 kilograms. The radius of the circle is 4 meters. Its speed is 6 meters per second. And gravity, of course, is 9.8. Our equation at this point, as we just worked out, was mv squared on r, the net force upwards, is equal to the normal reaction force up and opposed by the gravitational force down. So mv squared on r equals the normal force take away mg. We reverse this around. We're trying to make Fn the subject. So I add mg to the left-hand side, which leaves me with Fn equals mv squared on r plus mg. Let's substitute our values in. The mass was 2, the speed was 6, the radius was 4. The mass was 2 and gravity was 9.8. When we sub that all in, we end up with a normal reaction force heading upwards towards the center of curvature of 37.6 newtons. Finally, let's have a look at our tethered ball as it swings along the bottom. It's again got a gravitational force going downwards towards the Earth. There is a force of tension pushing it up, okay, operating on the string towards the center. Tension always goes towards the center. So we draw our green gravitational force, and then at the end of its head, we draw from the tail the addition of the tension force. Towards the center is positive. In this case, gravitational force is downwards. So when we add them together, we end up with an overall net force in the positive direction towards the center, which we knew we would because all circular motion generates a net force towards the center. As an expression, we have net force is equal to the tension force subtracting the gravitational force or opposed by the negative directed gravitational force. Expanding that into equation format, we have mv squared on r equals ft take mg. Our final example. A mass of 2 kilograms is being swung by a light rod in a vertical circle of radius 1 meter at a constant speed of 7 meters per second, as shown in figure A. So here we have our diagram with a rod of 1 meter with a speed of 7 meters per second. Which of the following directions A to F are shown in figure B? So here's our possible direction diagram. Shows the direction of the net force on the mass when it's at point P. So at point P, we are talking a circular motion, so we know that the net force always acts towards the center. So we'd expect direction D would be the correct answer. So the net force is towards the center, always in circular motion, so our answer D is correct. Let's have a look at the second part. Again, the same story as the mass is moving around. Calculate the magnitude of the tension in the light rod at point S down the bottom. So we want to show all our steps. So when the rod has swung around to the bottom, let's look what we've got. We want to know the tension, the magnitude of the tension in the rod. So the force due to tension is our question. The mass is 2 kilograms. The radius is 1 meter. The speed is 7 meters per second. And gravity is 9.8. So our equation down the bottom here, we know that the forces going upwards are positive. So that's our centripetal force, our net force, mv squared on r. It's equal to the tension in the rod moving up minus the weight force or minus the gravitational force moving downwards. So positive is centripetal force, positive is the tension force, and negative is the force due to gravity pulling it down. Let's rearrange this. We simply add our mg across the left-hand side. So now force due to tension is equal to mv squared on r plus mg. Let's sub our numbers in: the mass of 2, speed of 7, radius of 1, and of course mass of 2 and gravity of 9.8. Follow that calculation, we end up with the tension in this rod at point S, forcing up towards the center, is 117.6 newtons. I certainly hope this video has helped explain non-uniform circular motion in a vertical orientation. Of course, if you enjoyed this video, please like, share, and comment. And it'd be great if you could subscribe. Again, thanks for watching.